Добрый день.
Добрый вечер.
Да, точно. Да, точно.
У вас эхо. Теперь нет.
Сейчас поборемся. Предзащита 8-го, да? Надо, я приду
Да,
тоже.
очень хорошо. Хорошо.
Скорее всего. А что вы сейчас преподаете?
Ну, на ШАДе по-прежнему теория информации, только Леша теперь семинар ведет.
Она же и она сейчас идет? Или она?
Нет, она в другом семестре, осенью. А сейчас не идет.
А сложность вычислений больше нету там?
Нет, сложность вычислений мы отменили. Они как-то им не очень нравятся этот курс, видимо. Мы без обид его отменили. В мехмате я читаю. У нас ведь теперь магистратура появилась. Вы, наверное, не в курсе. А может,
Я помню, вроде было.
Но это вроде давно все.
Но наша вот это самая специальность, искусственный интеллект и цифровые технологии, только что вот они первые магистранты. А были, видимо, какие-то другие специальности. И вот я им читал алгоритмы построения анализа, а сейчас логику и сложность исчисления. И, собственно, придут, видимо, 3 магистранта. Можно
как студенты ваши.
Ну, они как бы под моим научным руководством диссертации пишут. Но это с большим натягом, можно говорить, диссертация, скорее это, ну, троечная дипломная работа.
Ну да. Это люди, которые мехмат закончили или какие-то другие?
Нет, конечно, никто из них мехмат не заканчивал. Трудно было закончить мехмат. Нет, среди них есть нормальные люди. Ну, в общем, никто мехмат, тем не менее, не заканчивал.
А ничего, что мы все это записываем?
Мы можем потом это
отрезать.
Обрезать. Я знаю как.
Нет, ну я вроде ничего такого не сказал, за что меня посадить можно. Так что можно не обязать.
Нет,
ну да.
Не обязательно писать такой донос, чтобы можно было посадить. Можно обойтись, значит, щадящим.
Ну, так скажем, наказать. Наказать вроде меня нет.
Ну, вы сказали только положительную вещь, что среди магистрантов есть нормальные люди.
Да, вот. Чисто положительно.
Hello, so when should we start?
Yes. Why not?
Yeah.
Okay, so I have just prepared a diagram of the classes I may talk about today. So some of them are well known.
Oh, good.
Some were introduced very recently. So my plan is the following. So during the first half of the talk, I will say about what all these letters mean, and then probably I will prove something non-trivial. Okay.
I'm afraid if you will try to explain what all the letters means, we'll never reach the second part. Maybe we should start with the second one, or at least.
Well, I think we should start with some general framework.
Yeah.
And then probably we'll, of course, we will skip something and skip a lot of details. But I want to say what it is all about. Okay, so in general, so what is the total search problem? So in general, we have some predicate v of xy. Oh, but by the way, sorry,
Yeah.
I can send the link. Sorry, where is this? So if you want, okay, here, if you want to draw anything, so you may join.
Yeah, you send the link in Zoom or?
I send,
Yeah, in Zoom.
Yeah, okay, good.
I think it should work.
Access to that board is restricted. Log in or start up to get started, they say.
I see.
No, we don't really need the access to this that board, so just we can forget about it, but it doesn't.
Okay.
Normally.
Okay, sorry.
Or maybe you should just subscribe to the service in general, and then they will do something.
Well, previously it worked.
Okay.
Okay.
So we have a predicate v of xy.
Yes, so we have a predicate v of xy. So usually it is polynomial. Usually polynomially computable. At least below FNP. So for FNP and for all below, it is polynomial computable. So above it is not. Okay, so usually a search problem. So a search problem is given x. Given x, find y such that v of xy is 1, or say that no such y exists. Okay, so and a total search problem is the one where y always exists. Total search problem. So here y always exists. Okay, so FNP is the class of all problems where v is polynomially computable. TFNP is the problem where y always exists. Okay, so FNP complete. So there is some type of reduction. I think I should not specify the details now, but
when you say problem, you don't use any formal meaning of this. It's just informal word, yeah.
An algorithm solves a problem if it does what is written here.
Yeah, so we just define what is FNP, And not we have kind of what is a problem, and then there is a special class of problems, like in NP is a class of languages, and here we just have a class of some things, which is called total search problem. Okay.
Yeah, what we see is a kind of a definition of a search problem. Just a search problem is one long word.
Yeah. Okay. But
Okay.
as usually, there are many we can imagine different types of reduction. So we can ask if one problem, we can reduce it to several cases of the other problems and then allow some computations or not allow computations or only one case or whatever. So it's not obvious what kind of reduction you want. There are many natural ideas of what reduction is here.
Okay, so usually it is something like a card reduction. In fact, there are two functions. So one function maps an instance of one problem into an instance of another problem, and the other function maps the solution of the other problem to the solution of the initial problem.
Yeah. But for example, the second function may also use the input.
Yes.
Because there is something similar in this Weyrauch reductions, and there are several Weyrauch degrees, there are several notions. Sometimes you are allowed to use the input, sometimes not. But here you're allowed to use the input.
Yes. Yes. Okay. Well, in fact, if I talk not about reduction in TFNP, but in FNP in general, then I also should say what happens if the answer is that no Y exists. Yes. For instance, I should be able to reduce a non-total problem to a total problem, and then from some characteristics of the solution of the total problem, I should be able to compute that no solution exists to the initial problem.
Yeah.
So this is why the definition is not very simple. And also there is the Knowles theorem, by Medgido and Papadimitriou. That if there are FNP complete problems in TFNP, then NP equals to co-NP. It is really not very hard. But the idea is that if I if I reduce, for instance, satisfiability to some total problem, then I can figure out then that the formula is unsatisfiable from some characteristic of the solution, and this would be a certificate for a co-NP problem.
No, that's not clear. But maybe first you should say, I guess it should be easy, why FNP complete problem exists. Just give an example of an FNP complete problem.
Well, in fact, every search problem associated with an NP complete problem is an FNP complete problem. Yes, so for instance, an FNP complete problem would be to either find a satisfying assignment to a formula or say that it is unsatisfiable, if it is unsatisfiable.
No, but what you mean associated? Just if we have an NP complete problem, it has answers yes or no. So
well,
we cannot reduce anything.
Yes, I see.
Just say something more specific and
yes, more specifically. So every NP problem is associated. In the certificate definition, yes, every NP problem is associated with some predicate V. So, for instance, for the satisfiability problem, I can take the easiest one. For instance, X is a formula and Y is an assignment, and V just computes the value of this formula on this assignment.
Yeah, so let's consider for V just Y is an assignment for satisfying assignment for formula X, and
Yes.
then we get a FNP complete problem for easy reasons, because if we have any other, we need to look for some Y. For fixed X, we construct a formula which is satisfied for just these Y's, and maybe there are some auxiliary variables, but and we can start with a circuit, for example. It's easier to construct a circuit, and then just this Y will be satisfying assignment for this circuit.
Yes.
That is clear, but if you want to make some general statement about all NP complete problem, this is not clear. Maybe it's not needed, but just as kind of reaction.
For every NP complete problem, such that the language, the problem is itself is equivalent. There exists Y for this particular V, that V of XY is true, and this V is associated with an FNP complete problem.
No, so if you take some NP complete problem, it's difficult in terms of existence of Y, but it's not clear why you can extract any useful information from this Y. That's what I don't understand.
Yes, so in general, this is even not true. But the true definition is that this V can be replaced by some V prime, for which this would be true.
Yeah, okay, but let's then if maybe this is not important, let's forget about this. Okay, so we know that there are FNP complete problems, and what about T and FNP complete problems?
Well, that's that's an open question. So TFNP complete, they are unknown.
Even assuming that NP is not equal to co-NP.
Even assuming, yes.
Yeah.
So the nature of it is like in BPP, because, for instance, in BPP, given a program, you cannot compare the probability with the thresholds, and here, given a program for V, you cannot determine whether it is total or not. So this is the problem. So this is why some generic constructions do not work. Yes, for instance, there is a generic construction for NP complete, like take a program or a machine tuning machine M and an input and some time limit, and say whether there exists Y such that this machine on that X and this Y returns 1 in this time limit. So here it is not possible because given a machine, we cannot check whether it is total or not. So this is why
we don't know about the existence of TFNP complete problems.
Yes, this is why simple approaches do not work, and no involved approach is known.
But what if we allow oracles? Then it's known or not?
Well, I think. Well, I think yes. I do not know an exact result, but at least something is known with oracles.
Even there is an oracle for which it has a complete problem. There is another oracle for which it has not.
No, if we have, for example, if we have an oracle like P space, then everything is
right.
It's like if P is equal to NP with this oracle, and then everything more or less, all these classes become trivial because we can check whatever we want.
Right.
But what about negative result? It's not obvious.
It's not obvious.
Kolya, you know something about this or not?
Yeah, we even have a paper on the subject.
Who we?
Myself and let me recall.
Okay, but more important, what was in this paper?
Well, there is an oracle for which TFNP has no complete problem.
Yeah. And how it's constructed? It's complicated or not?
As usual, it's not very complicated.
Okay, but if it's not, you cannot explain in 30 seconds. Let's continue then.
Okay. Okay, so usually people say some words like TFNP is a semantic class.
Because there is some condition in terms of there always exists something that it cannot be enforced syntactically.
Yes. Yes. So then the idea of Dimitrov in his seminal papers in 1994, I think. So the idea is, let us consider syntactic subclasses. So in the idea of these syntactic subclasses is the following. So consider some mathematical principle that justifies that the solution always exists. And this mathematical principle can be stated syntactically due to some reasons.
Yeah, for example, we can take Sperner lemma.
Yes, we can take that.
If there is a coloring of something, there is some error in the coloring. So we know in advance that for every coloring such a thing exists. Or if we have, I don't know, a graph which doesn't have an Euler path, we can look for a violation for a path or whatever.
More or less, this is exactly how it works. Yes, so for instance, we can use the pigeonhole principle or some lemma, or whatever, and more or less, so all these classes are defined by the underlying principle.
Yeah, so it's a very interesting kind of mathematical philosophical question. So we have some theorems. For example, we have I don't know, a fixed point theorem and Sperner lemma, and we know that we can prove one using another. So somehow it seems some topological results are equivalent to each other or combinatorial, and some are reducible to each other, and so on. And it would be interesting to understand whether this classification may be transformed to a formal hierarchy, and we can prove maybe that some theorems are easier than others. For example, if we have a Sperner lemma for one dimension, it's probably easier than
for one dimension. It is easier, yes, because in one dimension it is solvable by the binary search. But Sperner lemma in 2 dimensions and Sperner lemma in 3 dimensions are equivalent.
Yeah, that's counterintuitive, but
yes, that's counterintuitive, and it was discovered 10 years later than the equivalence of dimension 3 Sperner lemma and dimension k Sperner lemma, where k is greater than 3. So in this paper, Papadimitriou introduced some of the classes here. So mainly, so the central part. Yes. So let me draw. Well, so this part. So this part was introduced by Papadimitriou. So in 1994. So the others were added later. Okay. So I think I can briefly define what does it mean and what are the underlying principles. Okay, so well, probably the most important is this PPAD that stands for polynomial parity argument directed version, and there lies all this Sperner's lemma and Nash equilibrium and many other fixed point theorems. Okay, so so the idea, well, probably the simplest idea probably is in PPA. Yes, so PPA stands just for polynomial parity argument, and the idea is the handshaking lemma. Yes, so if you have a finite graph, then the number of vertices of odd degree is even. So if you have any graph, if you are given any graph and one degree of one vertex of odd degree, then there exists another one. Yes, so this is the principle of PPA. Yes, so PPA, if there is an odd degree vertex in a graph, then there is another one. So PPAD can be specified in so by various claims. So for instance, so if there is an unbalanced vertex in a directed graph, so then there is another unbalanced vertex. So then there is another one.
But what I don't really understand, so if we have, if we consider a graph where every edge may exist or not exist, then you can formulate PPA, but the checking that the vertex is odd requires exponential, graph is of exponential size somehow, I guess. So it requires exponential search, so it's not something which can be checked.
Yes. That's
so
true.
how do we define this PPA then?
Well, so there are two variants. So one variant is where all degrees are of all vertices are of degree are of degree 0, 1, or 2. So in this case, this graph is just a union of chains, cycles, and isolated vertices.
And for each vertex, we have a list of neighbors.
Yes, for each vertex is a list of neighbors. So a more general approach it is that the graph is exponential, but the degree of each vertex is polynomial, and then there is a circuit that takes a vertex and outputs all its neighbors. And also, in order to make it correct, an edge exists only if both its ends say that the other one is a neighbor.
So say it again, last thing, please repeat just.
Yes, so there is a circuit that returns the list of neighbors.
Yeah.
And an edge. So let me write it. So an edge, x and y is an edge. If simultaneously y belongs to the list of neighbors of x, and x belongs to the list of neighbors of y.
So we just artificially make it symmetric, yeah.
Yes, we artificially make it symmetric.
For PPA, and for PPAD, we don't need to do this at all.
No, in fact, we should do, because if we want to calculate the balance, then we must know not only outgoing edges but also ingoing edges.
In PPAD, we have lists of ingoing and outgoing.
Yes. In PPAD they have lists of ingoing and outgoing, and the same condition for the vertex.
I'm sorry, may I ask a question?
Yes.
These two approaches give the same class? Degrees 0, 1, 2 and polynomial.
Yes, that's a very good question, because yes, it is true both for PPA and PPAD, but for PPAD it was proved like several years ago, because Papadimitriou stated it in his paper, but it was a wrong result. So he stated for PPA it was proved for PPA, and he said that for PPAD it is more or less the same, but it is completely not the same. So the same approach does not work.
So I'm lost. There is very bad sound. Can you repeat, or maybe Misha can repeat the answer if he heard it?
As I understand, the answer is yes for both classes, but for PPAD it is a rather complicated result obtained recently.
And what is the result for both classes? The definitions?
Actually, Daniil gives us two definitions for each class. Either degrees are 0, 1, 2, or we have polynomially bounded degrees, so we have a circuit which computes the list.
Yeah, that's clear. But what is the equivalence then?
We have two classes, and these classes coincide.
No, but these classes not coincide. By definition, they are different. So we should say something in terms of reducibility or something.
So let me say, we consider just two problems. So one problem is that we are given a graph from chains and cycles. Yes, so with degrees 0, 1, or 2. And the other problem is when we are given a graph with polynomial degree. So formally, just these two problems are reducible to each other. So in the hard direction is that the problem with polynomial degree is reducible to a problem with finite degree.
And so the graph is given as a circuit, and then they are somehow reducible to each other.
Yes. Well, in one direction it is trivial, just a particular case.
Yeah.
But in the other direction, we should somehow transform the graph.
But actually, it means that classes are coincide, because for each problem, for more complicated problem, we can build this predicate such that we can define this graph and the corresponding predicate.
Yeah, what you explain is a reduction. It's not. They are just different classes of.
The problem belongs to the
Sasha,
class
the class is
if
defined
there
as
is a predicate V. By definition, as I understand. Maybe I
but
don't
V is very specific. V is just X as a graph and Y is the.
Yes, and for
there is nothing
one
to
definition, we can build up the graph of the second kind.
Well, usually just the whole classes are defined through the reduction. Say, for instance, PPA is the class of all problems that are reducible to this particular problem. And then, of course, if two problems are reducible to each other,
the classes coincide. Okay, but this is okay.
Now I don't understand the definition of PPA. So can
let me repeat the definition to check that I understand it correctly. So PPA is one specific problem, one specific V. Okay. And this V is X is a representation of graph in a special form. We have some number n, strings of length n are considered as vertices, and we have a circuit which, given the vertex, gives the list of 3 neighbors, of maximally 2 neighbors, sorry.
So X is interpreted as circuit. That
X is interpreted as a graph description in terms of a circuit.
Okay.
A circuit just represents this. It's important that it's not the adjacency matrix, because we need to know for each X we need to be able to compute the list.
Okay.
And this is specific V. And there is another specific V when we have
so sorry, and what is Y in this definition?
Y is another vertex which has an odd degree.
No, then you have to say that X is not only a circuit but also an
and also one vertex which is of odd degree. Yeah.
Okay.
And Y is another vertex of odd degree.
But if the vertex 1 is of odd degree, then it can always say Y is the first vertex.
No. Y should be not equal to X, of course.
Yeah.
We need to find another vertex of odd degree in a graph.
So, but in PPA, it has to be a specific other vertex. It needs to be connected or something.
No. Just any other vertex of odd degree, but which is different from the input vertex.
Okay.
Yes, if you want to have to find a vertex that is connected in the same connected component, then it is a p-space complete problem.
Okay, I understand.
Okay. Well, also,
but actually, to be formal in PPA and D, you have another parameter which is a degree of a polynomial, which is a maximal number of maximal size of neighbors list. So there is not one PPAD but several versions depending on the size of this polynomial. But you say that they are all reducible to each other.
Yes.
Yeah.
Okay. Also, I do not like the phrase that PPA is this problem. So usually it is not stated. So PPA is the class of problems that are reducible to to this particular problem. So the rest is correct. Okay. So what's next? So PPADS is more or less the same. So what the statement is that there is a vertex with so with the balance of the opposite sign. So the same as PPAD, but the another vertex must have balance with the opposite sign. Yes, for instance, we are given a graph and a vertex with a positive balance, and we should find a vertex with negative balance. So here S is a sinc because if you so in the problem with cycles and chains, so you have a source and you must find a sinc. Okay, so okay, now let us Well,
Same question. If you restrict yourself to this particular problem by source find a sink, is it equivalent to PPADDS?
It depends what is. I think if the capacities are flows are integer of small size, of polynomial size, then we can replace them by several edges. Not polynomial size, but of polynomial value. And
well, usually there are no flows, so you just have a graph.
It's just the same. You have a flow. So for each, from some vertex to some other vertex, there is some flow. In your case, it's 1 or 0 or minus 1.
Okay.
And then if you have a source, then you should have where all the flows are positive. You should have also some sink where all the total flow is negative.
But I don't understand. If we have a vertex of fan in and fan out 1, how to find unbalanced. So 1, 2 and 1, say.
Yeah.
How to find 1 or 2? How to reduce it to sink search, source sink problem? You are going to modify a graph exactly at this position.
When I say source, I don't mean that all the vertices are outgoing. I just mean the total flow is
and I am meaning the usual notion of source.
The flow is just opposite. Like
is 0.
If it was x, then it minus x. I don't know.
Yeah.
You mean that? But
yeah,
what
mean,
does the mean there? It means just if
it's
it was opposite, then it should be negative.
Problem. The vertex given is a source, so fan-in is 0, and we need to find the corresponding find a sink.
Okay, if you like this, if you have just some...
opposite sign. Sorry. Now I read the definition. Yeah, sorry. It's another problem. I don't know.
But you can also artificially add a source which just goes to this vertex.
I just put another restriction. Yeah. It cannot be expressed directly as a PPADS. If you have a source, how to find the sink? I don't know how to.
But if you require a sink that every vertex, every flow is ingoing, then it may don't exist at all.
Yeah.
So, you can have, if you have a
cycle.
Yes,
and plus...
yes. Agree.
Yeah.
Okay. So PLS is for polynomial local search. So here the principle is the following. So every DAG has a sink. So if if somehow you are guaranteed that no directed cycles exist, then also a sink must exist. But in this case, it is a different class.
It's semantic class. How do you say that? How you guarantee that something has no cycles?
So there is also a potential function, and so the edges exist only if the potential rises. So,
and just if you consider the problem, there is a function, and you need to find a minimal.
No. Well, so there is a graph. Well, there are various definitions, but in general, so there is a graph and there is a potential, and from this graph only a part is remained where the potential rises.
And the graph is with small number of neighbors again.
Yes. The graph is with small number of neighbors. Okay. So let me talk about the left part. So PWTP and PPP. So it is the pigeonhole principle. And
so who is pigeonhole?
So well, they're both pigeonhole. So PPP is polynomial pigeonhole principle, and WTP is polynomial weak pigeonhole principle.
And who is weak, polynomial or principal?
The principle is weak. Well, so for PWTP, so there is a circuit. So a circuit M that maps n bit strings to n-1 bit strings. Okay.
So it's kind of pigeonhole with factor 2 excess, and you need to find a collision. Yeah.
Yes, I need to find a collision. So and in the using pigeonhole principle, so the lengths are different.
Something is again with your sound. Maybe I don't know what is happening, but if you can do something.
Yeah, yes, I am. Well, is it better now or not?
So PWPP is pigeonhole principle with factor 2, and what is PPP?
Yes. Here. Yes. So here there is no factor. So there's just an negative term. So usually the task is the following. So I have to find a collision. Also find
So maybe it's a pigeonhole with just with small margin.
Yes.
Just 0-1 without 1 point or something like this.
Well, yes, like this. So I would say, or to find the pre-image of string. Yes, so here either x such that c of x is all zeros or all ones.
So you need either find that you have a mapping of n-bit string into n-bit strings, and you have to do one of two things: either to find a pre-image of zeros or to find a collision.
Yes. Well, it's trying to explain with other ways.
Yeah, and sorry to bother you, but it's my problem with the sound. Everyone is hearing okay or not?
No, it's my problem with the sound.
I cannot hear anything. I mean, it was very bad the last
But
minute.
maybe you can just find a mobile phone or whatever.
Or maybe if we switch off for cameras, it will be better.
No. I will join with another.
Okay, so while waiting, so it's interesting to get some classification to prove that some of these classes are the same and some of these are not. It would be interesting to,
Well, is it good now?
Yeah, much better.
Yeah.
Okay.
So you wrote many classes, but just tell us the secret. Are they the same or not?
Well, nobody knows, in fact.
Okay, even in the Oracle setting.
Well, in the Oracle setting, there are separations, at least for the old ones, and also
No, because I think it's much more natural to consider just the graph as a kind of Oracle input. So we have Oracle input, and then we transform it to another Oracle input by a circuit, a reduction circuit, which is then this interface circuit which connects it to the other problem, and then we can use the answer to provide the answer for there. And in this setting, it's more because if without this, we just may assume that P is equal to NP, and then everything coincides. But with this Oracle setting, I guess we have more chances to prove the separation. So what is known for this Oracle inputs?
Well, I don't know the complete list. Well, what I know that for some pairs, there are Oracle results that there exists an Oracle such that say PPA is not equal to PPND, and for many other pairs too.
Yeah. But is it a kind of difficult? It's very interesting in itself. So is it something difficult or it would be nice to learn this?
Well, unfortunately, this is not the part of the theory.
Yeah, but maybe Kolya, if you did something with this, maybe you know why something is not equal to something.
No, I don't.
You can look at complexity zoo, and there are some results. Say there exists an oracle relative to which PPP is not contained in PPAD. The result of 95 by Beam, Cook, Edmonds, and
So PPA is not is different from PPAD, yeah?
PPP is not contained in PPAD. For other classes, you need to look at.
So PPP, pigeonhole principle is stronger.
Is not contained.
But in other direction, there is a reduction.
In other direction, I see no result. I don't know anything. I just read the text.
Well, I think that the inclusion is true with any oracle.
And this lines mean inclusion in your picture.
Oh, yes. These lines mean inclusion. Yeah. So it's enough. Yeah. As for PPADS, I don't know, maybe, yeah, PPADS is in the list, but there are no results about inclusions.
Yeah, so for example, what it means in practical language, so if you want to prove the PPAD thing, you can reduce it to pigeonhole principle, but you need it with only one additional vertex. Is it somehow obvious, or imagine you want to prove PPAD? What do we do? And we are allowed to use PPP. What do we do?
Sorry, do you ask why this inclusion is true?
Yeah. Why PPAD is simpler than PPP, I guess. At least not more difficult. Yeah. So you can prove PPAD existential result by reducing it to PPP existential result somehow, informally saying.
Yeah, so the idea is the following. So let me show why PPADS is in PPP. So the idea is that just this, so just this C, this circuit is just the next vertex in the chain if it exists, or the vertex itself if it is a sink. So I somehow erase the isolated vertices. So then there are only chains and cycles. And I define the circuit that C of X is the just the end of the edge outgoing from the vertex, the end of the edge.
No, I don't understand. PPADS is just we have this vertices, and we have some flows. We have this numbers going from one vertex to another, and in some vertex this total flow is positive, and we want to find the other vertex where the total flow is negative. So what do we do if we use?
All the flows are equal, and also for every vertex, at most there is at most one outgoing edge. So we have only zeros and ones.
Okay.
So then we must obtain only cycles and chains, and just the image of X is the end of the edge outgoing from X.
So you consider the version of PPAD when you have only 0 or 1
in and out degree.
In and out degree, yeah?
Yes.
So PPADS, we don't know now how to reduce, just PPAD.
No, for PPADS, that's the same.
But PPAD, we can have many incoming and outgoing vertices, no? Explained.
Yes, they can, but firstly we reduce it to the case of 0 and 1 out and ingoing degrees.
Somehow we didn't discuss it, but somehow it's possible.
Yes, in fact, for PPADS, the initial idea of Popadimitri works, but for PPAD it is more complex.
Yeah. Okay.
Yes.
And for example, PPP and PWPP are not equivalent.
Nobody knows.
Even in Oracle setting.
When in Oracle, well, are there separations? Well, I do not know.
Mm-hmm.
Well, so what I read about is classification of particular problems, and also proves that some problems are complete in some classes. So let me talk a bit about this.
Mm-hmm.
Well, also there is a very interesting class P, TFNP. So because it is very close to TFNP, and I believe that both this, so PLC and PPAK, I believe that they also lie in PTFNP. And well, I do not know whether it equals TFNP. So here the first P stands for provable. So PTFNP is the provable TFNP. And here the main problem is the following. So if you have a proof in some logical system of a false statement, then there must be an error in this proof.
Okay, what is PTFNP? Just define it.
Yes. So PTFNP is the class of search problems that are reducible to one specific problem, wrong proof. So for this problem, wrong proof, so some logical system, like some light version of predicate calculus or something is defined, and then I have an exponentially long proof that is also defined by a polynomial circuit. And for this circuit, so this circuit generates a string like, so this string follows from this one and this one by such a rule. And in the end, you have two contradictory statements. So then there must be an error in such a proof. So, so one of the lines must not follow from what it claims by the rules it claims. So, and the task is to find the wrong line, so that violates the rules of the logical system.
And for different logical system, we have the same problem, or for every logical system, we have one specific problem.
Well, in fact, I do not know, because
no, you somehow say that let's take some logical system as if it was not important, and it seems quite interesting what is happening. If you take, I don't know, set theory and formal arithmetic, is it the same problem or not?
Well,
and why it's, for example,
well, in fact, so it was written in one paper. So in this paper, they created some
special logical system for that.
Yes, some form of predicate calculus, and then so they are Andrew Holberg and Papadimitriou. So and they have shown indeed that. Oh, sorry, I missed it. It's PPP. So for PPDS, it's also true, but what they proved is that PPP is in PTFNP. Yes, so so in that paper they show three results. So that PPP and PPA and PLS are subsets of PTFNP.
For some specific formal system.
Yes, for some specific formal system.
Is it a recent paper?
It's I think it's 5 years ago. Like
strange that complexity zoo don't know this class. It is maintained, as I know, and there are results of last year. It's strange.
Yeah, yes, it's strange.
No, but maybe if we didn't know that for different systems we get the same class, maybe then they don't consider it as something well defined to be included. I don't know.
I mean, if it is one paper, maybe, you know, people just don't always notice 100% of everything else.
Scott Aronson and Greg Kuperberg are very, very scrupulous in this case. There are 546 classes now in there, so.
Okay, then
it was 10 less maybe 2 years ago.
Yeah, okay, but I think now it's very interesting, a complicated picture, and now maybe it's time to prove something finally. Before we forget all the definitions, it's better to prove something, no?
Well,
we are very either a positive non-trivial reduction or a negative result would be interesting, but just choose something and maybe we can go and see what is there.
Well, well, I should think a bit what. Well, let me say something about complete problems, because so what people are interested about in complete problems is to state some problem that does not explicitly use any succinct form via circuit. Yes, because usually, so for example, what is the Sperner's lemma? Yes, for instance, I have some regular triangulation, and then I have a circuit that gives a coloring. And I should find an
error in the coloring.
Well, an error or a multicolored simplex usually.
Oh yeah, no, yeah, of course, yeah.
Yes. Yeah. Or also it can be said syntactically that there are no errors. Yes, so that the border conditions are satisfied. And then the task is just to find a multicolored.
Yeah. So what you say that usually a problem like this has some input of exponential size, and we agree that it's provided, for example, the coloring or the mapping in the pigeonhole principle or something else, and we represent this thing as a circuit.
Yes.
And you want to avoid this exponential size input or what?
Well,
when you say that you want to find a complete problem that is of some special type.
Yes. So for instance, consider the problem of finding a Nash equilibrium in a game. Yes. So a game is specified by a matrix. Not by a circuit that somehow encodes something exponential, but by a polynomial size matrix. Yes, so say a bimatrix game where there are two players and some polynomial number of strategies for each of them. And if one player chooses one strategy and another player chooses another strategy, then each of the players gets some payoff. And then there is a mixed Nash equilibrium. So there are theorems from game theory that there must exist, so Nash theorem that there must exist an equilibrium. And also in the case of two players, it must also have rational probabilities. Yes, so if so a mixed strategy is the probability distribution over the rows and columns. So two distributions on rows and columns of the matrix, and the so the values, the probabilities are rational with not very large denominators. This is why one can provide explicitly two mixed strategies, and one can check that they form a mixed equilibrium.
But yes, it's interesting because usually the Nash equilibrium existence is proven by using a fixed point theorem. And with fixed point theorem, we have no kind of warranty that the probabilities are rational. Something completely new.
Yes, well, it's a special bonus for two players. For three players, it is not so.
So you mean that for two players there is another proof of existence of Nash equilibrium for many strategies, of course, not two strategies, but there are two players, but many strategies and strategies, and still you claim that there exists kind of argument which proves that there are rational equilibrium.
Well, there is a rather elementary theorem that if there exists an equilibrium, then it must have rational coefficients. So
there's some another equilibrium should have rational coefficients, yeah.
Well,
I guess there could be a non-rational equilibrium. For example, if two strategies are exactly equivalent, we can just make any partition.
Well, in fact, if there is a finite number of equilibria, then every of them is rational. So otherwise, there could be some continuous segments of equilibria or something like this. Okay, so this is just because an equilibrium is a solution of some system of linear equations and inequalities.
So we use topology to prove that this system is solvable, and then we can use just kind of I don't know, elimination of quantifiers for reals and addition to get existence of rational equilibrium, assuming that equilibrium exists. Yeah.
Well, even you don't need such strong theorems. In fact, it just if you solve a system of linear equations, then you can use, for instance, Kramer's rule or something, and obtain that the denominator is not very large.
Let's skip another discussion of linear programming. Sasha Shane has a point here.
No, I just don't know the argument. Maybe anyone else knows, but okay.
Well,
so what you say?
You can read books. There is a Scriver book on linear programming. You can read the proofs.
No, there are a lot of books which contains a lot of wisdom.
Yes, but you reject exactly books on linear programming, not in other things.
I try to reject everything, but okay. Let's.
Yes, in fact, there is a very beautiful Lemke-Howson algorithm, but so it is close to linear programming and to simplex method, but it exactly gives such chains and cycles like in the definition of PPAD. But there is a hard part in the degenerate games where there is a continuous sets of equilibria, and it should be somehow tuned. Okay, so nevertheless, so the Nash equilibrium is the example of so-called natural problem that is PPAD complete. Yes, so there is no explicit circuit, and still it is PPAD. So in some.
So if we now want to solve some PPAD problem with Oracle, now we cannot reduce it to Nash equilibrium because there is no place when to connect the Oracle. Yeah. So normally the reduction is kind of Oracle reduction, I guess. So we can just, if we have an Oracle input, we also can make a reduction. Here there is no way to make it because there is no Oracle input in Nash.
Yeah. Well, probably.
Okay. Yeah.
Okay, so there are two recent results with natural complete problems in PPA and PPP. So in PPA, well, I should not state them in details. Yes, so for instance, so natural complete problems.
It's very interesting indeed that you can kind of avoid Oracle. It's very unexpected thing.
Yeah, so in PPAD it's Nash equilibrium. So in PPA, so the there was a paper in with some PPA complete problems, but they were something like this. So we know that Sperner's lemma on a simplex is PPAD complete. But now let us consider Sperner's lemma on the Möbius strip. So somehow define the boundary conditions, and then it is also true on Möbius strip. But since there is no orientation on the Möbius strip, then it would then we would be unable to make the graph directed. So, but also there is a well, there is also a story with discrete analog of Tucker's lemma. So it is another yes, another mistake in Papadimitriou's paper. So he claimed that it is PPAD complete, but it turned out that it is only PPAD hard, and it is not in PPAD. And in fact, it is PPA complete. So and then so this Tucker's lemma is close.
So now you want to explain a natural complete problem in PPA, or what?
Yes.
And what is about Sperner lemma for Möbius strip, whatever it is? It's related to this or not? You say something, but I don't understand the connection.
Yes. So it is an example of a PPA complete problem that is not trivial, but also is not natural.
Not natural PPA complete. Okay.
So the consensus, I think, is. So consensus halving. So what, how is it spelled like this?
Halving, я думаю.
Halving, yes, but consensus is for
I think yes, yeah. Consensus. Okay. I don't know, but.
Yes, I hope so. Okay, so consensus.
So what is this?
So consensus halving is from the fair division area. So here the task is the following. So there are some k measures on a segment. So and these measures are somehow partly linear or something like this. And so these measures are interpreted as so some tasters on a cake, and the task is to to cut this cake into several parts, and then somehow arrange these parts into two groups, such that by any measure these groups are equal. Yes, so cut a cake into some, well, I don't remember how much, so some polynomial number of pieces, and rearrange them so such that into groups, arrange into groups, so such that the groups are equal by each of k measures. Yes, so the classic task of fair divisions is, for instance, the NV3 division. Yes, where you cut the cake into n groups and arrange them among n agents, such that every agent thinks that their part is the best one. So and it is PPAD complete. So here consensus halving is PPA complete.
So the input is just the densities is of prices according to agents are piecewise constant. Yeah.
Yes.
And then you want to cut into halves, and each half should be a set of segments, of subintervals.
Yes.
And
yes.
so you say that it's always possible with the polynomial size of the number of subintervals and polynomial rational numbers as boundaries. Somehow. Yeah?
Something like this. Well, probably there is some, well, probably they are equal up to such small epsilon.
No, so you are looking for approximate solution with given precision, or you are looking for exact solution?
Well, I don't remember.
If you don't plan to give us the proof of this, then
no,
it doesn't matter really, because we should understand it anyway. But if you want to prove something, of course, we need to know exactly what you are proving. But
yes, of course. But in fact, here the proof is very complex.
Okay. So what is the simplest completeness proof for some natural problem? It would be just a very interesting. It's a bit like arithmetization in IP and P space, because we somehow finally really use that we have an oracle which is not abstract, but it's given of a circuit. So it's something very, very, very non-trivial somehow. This idea of natural complete problem. So what is the simplest, maybe is there some natural complete problem which we can really understand the proof of its completeness, or it's still beyond our
well, in fact, so this talk is based on my course in MIPT.
Yeah.
So where we proved something, and in fact, so for Nash equilibrium, it was something like 4 lectures or 5 lectures. So for
can you just maybe say the main idea? So you start with a circuit. So how you use that? It's really a circuit, not an arbitrary function. So you need to encode the circuit into something, analyze the structure of the circuit, or do something very, very non-trivial, I guess. Yeah.
Well, I can present the idea for Nash equilibrium. Yes, okay. Because it is a complex proof, but it is split into some stages.
Yeah. So just the main thing. So you start with a circuit where you do use the fact this is a circuit, not an arbitrary oracle. What we can imagine is all argument like this. So if you have, I don't know, a coloring, then you consider a function which is, we look for a pigeonhole problem, hash collision, and then having a collision we get a coloring, and or always we transform something oracle in some way.
Sasha,
yeah,
why can't we use the circuit as oracle?
Because we need to use the fact. We can kind to go inside the circuit and understand that it's made of specific elements. To get something where there's no exponential things, we need to use not the behavior of the circuit, but its internal structure.
For a reduction, we need another thing. We should construct somehow a complicated game, which simulates an arbitrary circuit.
Yeah, and for that we should look inside the circuit, not yes. in its behavior. This is exactly what is very.
Yes, but some construction may use the circuit. You have a circuit and you construct a game by.
Yeah. That's exactly what's interesting.
I guess that we use a circuit as a black box.
No.
How can we then, if we use it in a black box, then we the game will not be. we need to construct a polynomial size table, and the black box has exponential input, so we cannot use the black box behavior. It's here where there is a very interesting moment.
Well, the general idea is the following. So in the games, so the idea is that first we create some small game that models one gate of the circuit. So for instance, so the so the equilibrium corresponds. Well, so there is an equilibrium only if so say the strategy of one player is, for instance, the product of the strategies of the other players. Well, probably I can show an example.
So you construct a game for each gate in a circuit, and then somehow you combine this game in such a way that the total size remains polynomial, which looks unbelievable, but
yes, I combine these games, and then I crucially reduce the number of players. Yes, because more or less initially I have for every gate of the circuit I have, for instance, 4 players. So and I obtain a very large game with a lot of players. But then I crucially reduce the number of players. So initially it was reduced to 4, then to 3, and finally to 2. So that there was a process.
No, if there are 4 players, we still have a polynomial size matrix. So it's already natural problem.
But we don't have this result about exact rational solutions.
Yes,
we should consider approximate Nash equilibrium.
Yes, of course. Of course, if there are more than 2 players, then we should consider approximate solutions. So, and then this is why people thought that the result is different for 2 players, but it turns out that it is still PPAD complete. So it is not simpler.
And this is the simplest natural problem you can think about.
Well, I do not know. Well, so in fact, so for PPP, for PPP, the formulation of the problem is more complex, but the proof is simpler than for PPAD and PPA. Well, so for PPP, it's from the lattice theory. Yes, so SIS is a short integer solution. So there is some very specific problem, but still there is there is no circuit. There are only matrices.
Yeah. So what is SIS? Just can you explain, or it's too complicated to be understood? No, maybe since we have only 5 minutes remaining, maybe for you can if there, I would like to hear more. So I would quite happy to meet in a week, because there is no other plans for the seminar for a week. So
well,
we can just have
there is a holiday.
And next, yeah, and so tram doesn't work, and so you cannot go anywhere. So it's very natural to have to celebrate this by considering a small integer solution. But if you have other plans, of course, you know.
Well, well, probably I will be in Sochi, but probably I will be able to.
Okay, so just what you. No, I understand what I understood before, that there are these classifications of different existential problem and reduction for each other. But there, the idea of natural complete problems is completely it's much more. It's kind of something unbelievable. So if there is something understandable in this whatever class you want, to get the argument as simple as possible, but something with Oracle should be reduced to something natural, and this would be a really interesting thing, I guess.
Okay. So,
it's because you consider these classes as Oracle classes. If you fix Boolean circuits, this miracle disappears. Boolean circuits is a combinatorial thing. It can be transformed into another combinatorial thing.
No, but okay, okay, but usually, no, okay, but it was a great step when it was found a non-relativizable result about normal complexity, about circuits or whatever. So here this big step is already made, and I think it's very interesting how it's made.
No, I agree, it's interesting, but I think it's not so important as arithmetization.
Okay. No, I cannot compare these two things, but it's kind of similar thing as finding something which is not relativizable by construction.
Yeah, I agree that any statement which is not relativizable in computational complexity is interesting, but maybe we should slightly tone down when we talk about it, because it was a great discovery 40 years ago, and probably now people get used to such events, so they're not that impressed. So it's also normal. If some of these statements are not only non-relativizable, but also they somehow beyond the algebraization barrier, or some proofs are not natural in the sense of Razborov and Rudich, then of course it will be even more impressive.
I have a parallel to NP completeness results. Suppose we have NP completeness of a problem solving some quadratic Diophantine equation with two variables. There are no circuits and no Turing machines in quadratic Diophantine equations. There are only 3 integer coefficients. And of course, it's very strange how to encode some program to these integers, but it's possible. It's a very ancient result. And to me, Nash equilibrium completeness for PPAD is something like this. It's interesting, but it's not so important as arithmetization.
No, but in here you just combine a polynomial amount of information into no, okay. Okay.
Compare with this Diophantine equation problems. You have 3 integers. There are no natural way to encode a program by 3 integers, but there is a reduction.
Okay, no. I think that there is something more, because we switch from we use something not as a black box, and it's rare. But okay, but. No. Anyway, it's not. If you agree that's interesting, that's enough to ask Dania to explain something. But maybe you can use the simplest possible, maybe even not the complete problem. We are very we are not picky. So just take some problem which some class which is reducing to some natural problem. Maybe this natural problem within another bigger class. But that's okay for our first step. But what is nice that we just have a problem which includes some exponential object presented by a circuit, and somehow we reduce this problem to something which has only polynomial size input.
So yeah, the only question which remains is whether there exists a simple result of that kind. So we have a long discussion of how it would be great to have an explanation of such a result, but then the question is,
but
if whether
the
all of
weaker
them
are
take
requirements for the
lectures.
results, the more chances of its existence. So just
well, I think, look, so if you well, probably I should look down at the smaller classes. Yes, because for PPAD it was created like 18 years ago, and for PPA and PPP like 5 years ago, probably. But these lower classes, so they were invented later. But probably I should look at them, and probably very
or just what.
Well, well, about constraint SIS, well, I can't formally prove it, but it's not a very pleasant topic. So there are some matrices.
Okay, no. If there are matrices, it's unpleasant. I agree. but then, okay, but then just try to think what can be done. Even if you prove that FP is reducible to some natural problem in much higher class, whatever you want. Just something with exponential input reducible to something natural. Okay, so
well, FP is just solvable in polynomial time.
No. I thought that there exists unique Y, that there could be a case when for every X there is a unique Y, and you need to find this unique Y. But
yeah, so this is close to this.
It's U.
It's
something else.
Yeah, it's another.
So here
okay.
Unique end of potential line.
Okay, potential line. Okay, so just choose whatever you want and prove something simple, or at least feasible, if not simple.
Okay, I'll think about it.
Yeah.
Well,
So
I think on my first, I will not be able, because it's also the deadline for camera ready for CIE.
Okay, no. Of course, if you are not, but Kolya, you say that you wanted to have your students' talks. You suggested to have it 8th, but maybe we can have it at 1st May, and then to have 8 for Dania, and 15 May we will have Babianka.
1st of May is not good, because I think that their thesis will not be ready.
But no, there are more, and there are more chances to have strictly more chances to have them ready at 8th.
Yeah, right.
Okay, then we have no choice, and we have to declare so 1st of May, maybe if Dania somehow has a chance to if you want to prove something, we will be glad to hear you, but by default we will have no meeting at 1st May, and also we will at 8th May we will not have a meeting of a seminar, but instead we will have used this time for giving a formal hearing of Vereshchagin students, and this will be have at 8th of May in normal time, like 5 o'clock.
In Russian.
And in Russian, because if it's even in Russian, it will be unclear. So let's not. It's not a seminar meeting, just a kind of using a hole in the seminar schedule. And
just excuse me. Just I don't understand this comment about the language. I read in the email that some of these students are not Russian, so it's not their native language. Maybe for them it's easier to to speak in some other
their
language.
native Chinese language. Okay, maybe
Chinese,
what
for
we will
example,
do.
yeah.
I'm afraid, Andrei, you won't welcome Chinese.
Yeah, indeed.
No,
If it's Chinese,
me either. But anyway, this will be a special event, and we apologize. It's not a seminar meeting, so probably it will be more formal hearing than something really mathematically interesting. But just it will be at 8 and 15. We will Maxim Babenko will explain what they did in MapReduce open software in Yandex, and also there will be a chance to ask any questions to him and Ruslan Savchenko,
Sponsored seminar.
Another participant of our seminar, and he will Babenko, and he was also in this group who developed this open software, and then they will come at 15th of May and we'll talk about this.
And on May 22nd, the semester is off.
No, maybe something will be. No, no. Maybe if you will be ready at that time, we can try to plan your talk. But there is some still some.
Okay.
By the way, I got a message from our French authorities that Georgia is a risk. So there is a special procedure needed to organize a visit there. So yeah, it's not.
Well, I think because for formally not all of internationally recognizable Georgia is controlled by Georgian authorities, they should check that you will not go to Abkhazia.
Okay, no. It's still okay. Maybe, but.
Yeah, just no. Seriously, I think you must specify the fact that you do not go to the territories that are not controlled by the government.
They sent me a message that say Batumi, Adjari, Georgia. I don't know. Adjari is not Abkhazia, I guess.
Adjari is not Abkhazia.
yeah. No, but for example, if I want to go to Japan, it's still not pay, I think not pays a risk, because still it doesn't control some part of which it would like to control. So it's not clear whether this is the only reason for the obstacle. Okay, so any questions to Dania for now or?
I have a question, but maybe it's there is no short answer. I would like to understand the relation between these different kinds of problems that there are. Distinguishing problems with the answer yes and no. There are search problems where the answer is an element of and bits. There are sampling problems, and just it would be nice to know what is known about the relations between these kind of problems. So can we transform a search problem in a sampling problem in a decision problem, or vice versa? Because typically all the courses of computational complexity, they are all about complexity of Boolean predicates. But it seems that the search problems are as natural as predicates, maybe even more natural.
Probably even more natural, yes. Well, I include basic search problems in my courses of computational complexity. Well, in general, so it is clear that decision problem is reducible to a search problem. Yes, because here what is answered contains where this y exists or not. So the opposite direction is true for NP complete problems. Also, so with some conditions. But Well, I think it's rather well known that if you, for instance, if you know whether there is a click or there is no click of such size, then you may find the click of this size.
No, it's just I think old Levin remark or old of.
Yes. Also, for instance, for graph isomorphism, it is also true. So if you can, well, it's about Cook reduction. Yes. So if you can check whether the two graphs are isomorphic, then by polynomial number of calls, you can check whether you can find an isomorphism. But also it is clear that for total problems, so the decision variant is trivial, but still the search may be hard. Well, as for sampling, in fact, in the paper about constraint SIS, so there are some talks about cryptography and something worst case to average case reductions, but I have not yet understood it well, what is written there. So probably it is somehow connected to what you're asking about.
Yeah, okay, so any other? Okay, then thanks again. And we hope finally to hear at some point this reduction, but no fixed date.
Okay, yes. I will think about it. Thank you.